This is chapter 14 and 6. And the solution of the differential equations. Is describing the circuit. This is about how to solve the electric circuit using Laplace transformation. For this, we have discussed about what is Laplace transform in the previous chapters. So this is process to solve a circuit using Laplace transform. First, derive the differential equation from circuit in the time domain. This is a common things we have discussed in the previous semester in chapter 9, chapter 8, chapter 7 maybe, 7, 8, 9, and 7, 8 and 7, 9. We have discussed how to solve the first order electric circuit, the second order electric circuit using differential equations. So this the process 1 is the same, is common. Because the Laplace is kind of a tool to solve the differential equations very simply. So at first, to analyze the electric circuit, we need to make a time domain the differential equation at first. The second, the Laplace transform. Of the differential equation. And third, we can get solutions. It's quite simple. Actually, calculate the solutions. It's not. First, the inverse Laplace. To get the solution in time domain. So this is a simple process. Is to using Laplace transform for another. So we'll give you some example. Example 14 and 6 and 1. So find the VCT. The circuit is very simple. We have one voltage source and one resistor, an inductor, and one resistor, and capacitor here. So it's quite simple. This R2 is 5 ohm. And C was here's another point. C is 10 millifarad and L is 2.5 Heli. It's quite a big inductance in zero system. L is 1.2 ohm. Sorry, it's not 1.2. It's 15 ohm is R1, and this is VI. And your VI is 10 plus 10 UT. Defined current is ILT, and this is our voltage is VCT. The question is how to get what is a VC in time domain. We know that this is a second order differential equation. The second order system, so we get a second order differential equation to describe that is a second. So that means we need at least two initial conditions. Generally, in the case of electric circuit, in the case of inductance, we need the inductance initial current. In the capacitor case, in case of capacitor, we need initial voltage of capacitor. So in problem, there's some variable are given. IL 0 minus is 0.5 ampere, and VC in 0 minus is 2.5 volt. So this is a solution. So one step to solve these equations, you know that first the derive equations, second make a Laplace transform, third calculate the solution based on Laplace transform, and fourth you get a time domain solution through the inverse Laplace transform. So at first we will describe the system. So how can you do that? We need to make two variables in this system, like capacitor and inductor circuit. And in the case of inductor, we need to make a variable as inductor current, and one is in voltage of capacitor. So based on that, at first we can describe the IL. I mean, to do that, we need to get the this current here. The same is this current and this current. This is IR2. This is IC. So IR2 is VC divided by the R2, because this voltage is VC, and IC is C dTd VC. Because of KCL, IL is same with IR2 plus IC. So therefore, that is VC over R2 plus C dVC dt. So first equation is ILT is R2 VCT plus C dTd VCT. And Next is free C. I mean, to get the free C, including we have one more equations, that is including the VI. So VI, this voltage same with this voltage and this voltage. So VIT equals R1 ILT plus LTD ILT plus VCT. This is number 1, this is number 2. This is a step. Then what should we do? The step 2 is Laplace transform. And here we can do that. Equation 1, we rewrite, we defined the Laplace variable of ILT is capital LS will be R2 is constant. So 1 over R2 and VCS plus, you remember that dTdF Laplace was SFS minus the initial value of that. So we can write here is, can write this term is C S VCS minus initial value of capacitor voltage here. The second, VIS will be R1 ILS plus the same reason we get it, that is SILS minus initial value of current plus VCS. So actually we don't know what is the value of IL and IC in the Laplace domain, but anyway we got this. So we define this number is 3 and this number is 4. Then we can do that. Here, so VIS will be R1 plus LS, this is a ILS minus LIL plus VCS. We cannot solve the equations. Why? Because there are two unknown variables. There is a IL, unknown variable is, here unknown variables, ILS and the VCS. So we need to identify what is ILS and VCS. So from here we get insert the equation. Oh, we need more space, so I think we will remove another page. So we insert equation 3 to 4. Then VIS will be R1 plus LS. Instead of IL, we insert this variable So 1 over R2 VCS plus CS VCS minus C initial value minus IL initial value plus VCS. So we can rewrite simply because there are one variables. Where is that? We have VCS, VCS, VCS. So we can rewrite here VIS is LC S square plus no, I need to some procedures. First, what we'll do is in this way and in this manner. So that is R1 over R2 VCS plus R1CS VCS minus R1C VC initial values plus LS over R2 VCS plus we have C and L and LC and there are two S square VCS minus LCS initial variable capacitor voltage minus LIL initial value plus VCS. We have some VCS, and VCS. So we can simplify this based on VCS. This is LCS square, and there are S square and S here. So can we write here is L over R2 plus R1CS, and the main thing is this and this. So plus 1 plus R1 over R2 VCS minus the initial value of here is that and that. So that value is minus LCS plus R1C we initial value minus LIL initial value. So this is Laplace equations from the circuit describe the equation in time domain. Okay, then step 3. Step 3 mean first, second, and this is step 3. Calculate the solutions from the Laplace equation. So we get some solutions. Now to that, VIT was 10 plus 10 UT. That means it's 20. It's 10. At T is here, but here is 20 values because of UT. Therefore, Therefore, the Laplace transform is constant, only the time is the larger than the 0 plus. So here vi t was 20. Therefore, the Laplace transform of the source, Laplace transform of vi is a vis, because there's 20. Laplace 20, so that is 20 over s. So we need to think about this equation. This is their values. So we get the 20 over s will be, we insert some variables L and C. L was 2.5, and here L is 2.5, C is 10 milli, that means 0.01. So the result is 0.025 s squared and plus 2.25 and 5 plus 0.015 s plus 1 plus R1 is 15, R2 is 5. The VCS minus LC, the same reason, 0.025 s plus 0.015 VC. Initial value of VC was, VC was 2.5, so that value was 2.5, and current value of initial current value here is minus, inductance is 2.5, and current initial value is 0.5, so 0.5. So can rewrite this equation is s over 20 over s was 1 over 40 s squared plus 26s plus 160 VCS minus 1 over 40 s plus 6 2.5 minus 1.25. So we need to simplify this equation to get the VCS. So 1 over 40 and s squared plus 26s plus 160 VCS was 20 over s plus 140 2.5 s plus 6 plus 1.25. So s squared plus 26s plus 160 VCS equal to 800 over s plus 2.5 s plus 65. So from there we get the simple VCS was 1 over s squared plus 26s plus 160, and we make some equation. S was 2.5 s squared plus 65s, this is 2.5 2.5, 65s plus 800. So we can simplify this. Is s and s plus 10 and s plus 16 and 2.5 s squared plus 65s plus 800. So then what should we do? We need to make factorize. So we need to rewrite this is this is a 3s. So you can get this is a r1 plus s plus 10 and r2 plus s plus 16 and r3. So we need to figure out the value of r1, r2 and r3. So how to get the r1? You know that r1 is same with multiply s and VCS, then s will be 0. So we have already known that we can write the system here, system like that, and multiply s. So this will be eliminated, and adding s is 0. So the result will be 0, 0. The result will be 10, 16, 800. So it will be 5. In the same way, R2 will be s plus 10 VCS, then adding s will be minus 10. So the result was minus 6.67, and R3 was s plus 16 VCS, then s will be minus 16. So the result was 4.167. Therefore, finally, VCS will be s 5 minus 6.67 s plus 10 plus 4.167 s plus 16. So that's the solution in the Laplace domain. Then the last step, step 4. Step 4 was inverse Laplace transform. Why? We want to get the time domain solutions. So VCT was inverse Laplace transform of VCS, and that was 5 over s minus 6.67 s plus 10 plus 4.167 s plus 16. So the first term is 5, second term is minus 6.67 exponential minus 10t, and plus 4.167 exponential minus 16t. So t is less than the 0. Actually, this is plus. So this is solution. So to check this variable in problem, initial value of VC was in problem was 2.5. So it was 2.5. we need to check the variables. So VC 0 plus was 5 minus 6.67 plus 4.167. So there is approximately 2.5. So this is the way how to solve the electric circuit using the Laplace transform. In the previous, the time domain, the differential equation solutions lead to very complicated the steps. At first, we need to get the force response and neutral response, and we need to calculate the initial value to find out the parameters in the solutions. So that's a little complicated. But if you use the Laplace, we don't need to solve the differential equation in time domain. It's very simple and it's very powerful to solve here. But the Laplace transform has very strong method to solve the differential equations. That is not only the solution in that is not only the very powerful solution to solve the differential equation, but also the Laplace transform give us a very big insight about the system. Because we already deal with about that. There was the network function using the Phaser. In the Laplace transform case, we call that is a transfer functions. The transfer function does not apply not only the electric circuit, but also all systems, the mechanical, the chemical, and whatever it is, the system can be represented in the Laplace, the transfer function, if the system has a differential equation. So, especially in here, we will discuss about how to analysis in the viewpoint of in the electric circuit, in the viewpoint of Laplace transfer function. From there, we get a very useful insight about the system, and very simply. So to do that, before that, we need to discuss about what is the impedance in the viewpoint of the Laplace. So that is chapter the circuit analysis. So using the impedance and an initial condition. So in the case of the Phaser, we need to only apply the source is a sinusoidal. In the same way, because the Phaser has the assumption that the state is a steady state, so they does not care about the transient response or the initial conditions. But Laplace is a very huge system. Very huge system. So what do we have to do using the Laplace? Okay, in the Phaser case, the Laplace is more huge approach to analysis in the frequency domain. In the case of Phaser, the Phaser approach, so we can apply only sinusoidal source. electric circuit. And we can get only the steady state response. And the Laplace is more the approach. Laplace can variable various the source, like the step, sinusoidal, exponential, and whatever it is. And we can get not only the steady state but also the transient response. So Laplace is a more powerful and more general approach to analysis the system. The system not only the electric system but also the mechanical and other chemical, whatever it is, the system can be, if the system can be represented in the differential equations. So to analyze electric circuit based on the Laplace, we need to define the impedance. Impedance of Laplace represented is, you know that the impedance in the viewpoint of the pager was defined as G omega. The impedance is a function of frequency in the pager case. But in the case of Laplace domain, the impedance can be represented in the S. So there is a definition of Vs divided by the current in the Laplace. So at first we will see the resistor. The resistor case we define in the time domain. This is a Vt, and this R, and this current It here. Then relation is Vt versus It. Then what can we do? Just put Laplace. Then that variable will be Vs and will be constant value of R and Is. So therefore GR, R's impedance of Laplace is the same as R. And the second thing is capacitor. So in time domain, capacitor was defined like C, and voltage is Vt, and current is It. Then the relationship between the voltage and current and the capacitor, so that was It or C dt Vt. So we will do this in the Laplace. So that was, we'll use red pen. Is is a C S Vs minus V0. So we can rewrite this as from the Vs was 1 over C Is plus initial value of capacitor. So therefore, oh no, we're missing S. Therefore, Vs was 1 over SC Is plus 1 over s initial value. So we have two representation of capacitor in the Laplace, and this and this. So we can rederive this is a Laplace equivalent the second. Once in the case of the first, we can define here, that is, if you use, that is is was c s vs minus initial value. That means we can derive, there's some port here, there will flow is and is something like that and something like that. The current source, that value will C to initial values, and this is a one of SC. And the voltage defined in here is Vs. So this is one model of capacitor in the Laplace transform. And second thing is Vs was 1 over SC is plus 1 over S initial value of V. Then you can derive this is in this manner. This is a Vs, and that is a 1 over SC, and current is is, then the voltage source was initial value over S. So we have two models to represent the capacitor in the Laplace domain. So if initial value is 0, the model is very simple. In that case, the Vs, capacitor voltages, which can be represented as 1 over SC is. In this case, GCS can be represented as 1 over SC. Then you can derive capacitor is 1 over SC, then Vs, and current is is. You remember that in the Pager case, what is the impedance G omega? Was my J omega C, 1 over J omega C. In the case of Laplace, is 1 over SC. J omega represent is S. Actually, I will always tell you that the Laplace is more used the approach to describe the frequency, the domain. So why? Because, remember that S is a complex number by the Laplace. So S can be represented as R plus J omega. So the Pager is a kind of a subset of Laplace. In the Pager case, we define R is 0, then that will be J omega, then decreases Pager approach. So very similar with Pagers and Laplace, but Laplace is a more general approach to analysis in the frequency domain. So anyway, capacitor can be represented as 1 over SC. And third is an inductor. Inductor was present in time domain is L, this is V, T, the current is IT. So we write more simple. So in time domain, inductor was Vt was L Td It. Can you place? This is Laplace. Then you say, so we write the capacitor case in the Laplace in this manner. The same way you can do this. The Vs was, and it will be L, because the derivative of Laplace is S, Is minus initial value of it. So in the same way, we can derive the other forms. Is can be represented as 1 over Ls and Vs plus 1 over S I current initial values. So we can make a same Laplace equivalent circuit in the capacitor case. We can do this in the same manner as a Laplace is equivalent the circuit. That is based on the equation, it's model. So to do that, we need to do that here is in this manner. We draw the picture, the circuit based on the equation in here. So we'll do this the same way. Yes. First, Vs was L SIS minus I current, initial current. So based on here, this inductance here, there will be LS, and there are some voltage source is L initial current in here. This is current is IS, and this voltage drop is Vs. So from other equation, Is was 1 over Ls Vs plus 1 over S current. So the current is sum over here is inductance and some current source. There will be 1 over S initial current, and this current is Is, and this is a 1 over Ls, and this voltage is Vs. In the same way, if initial variable I0 is 0, then Vs is simple Ls Is. Therefore, GL, impedance of inductance, was Ls. You remember the Laplace case, G omega was J omega L. Instead of J omega, we insert this S. Let me write this is SL. The next is the dependent source. That is, if there are some current here, so this is ICT, we define this name is ICT, and we make dependent voltage source. This is IT, and this voltage source VT can be defined in the manner of K ICT. Then you will transfer, so this is Laplace. Then it's very simple. Just using the current can be represented is a Laplace through the Laplace transform of IT, and we have also some voltage source. Dependent voltage source is the Laplace VCS was KICS because of this constant. So Laplace transform constant is constant. So can represent in this circuit here. The current is IS, this is IC. How about the OP amp? OP amp, we can use same topology, same approach. You know that if you get the OP amp here, then inputs and outputs, this voltage is the VT. Then we have some assumption. What is that? That is a voltage difference is a 0 volt, and this current is a 0 ampere, this current is a 0 ampere, and if this is IT, then this can be represented in the same manner in the Laplace minus plus, and here this voltage is VS, this current is IS, and this is a 0 ampere, this is a 0 ampere, this is a 0 volt in the Laplace. The same in the case of time domain in Laplace transform domain. So I will give you some example to using this characteristic of the element in the lattice circuit. So first example 14 and 7 and 1, and find the C values. So what value of C? We have some circuit, it's a switches and one register, and one more register, one capacitor here, and there's some source, a simple 20 one more register, and it's the C. This is 2 ohm, this is 4 ohm, this is 18 ohm, and switch is closed at T is 0, and this 24 volts. Then define this is VOT, output voltage. Then actually VOT was 16 minus 12 exponential minus 0.6 volt, and T is less than 0. Then to satisfy this output voltage, we need to define the capacitor value of C. That is a problem. So we need to rewrite this circuit in the Laplace domain. If we know that the T is less than 0, so there are one source, and because T is closer than 0, so it is connected through the switches, so we don't care about these registers. So that is a constant 24 can be represented in the Laplace 24 over S, and this impedance is 4. So in the case of Laplace, this is 4, and also this is register, so the value is 2 because this is register, And we have one capacitor and series of voltage source here. Why? The capacitor's equivalent circuit is looks like that. So represent capacitor is like that. So that value was 1 over SC, and that value is 4 over S. Actually, why this is 4? Now you know that V0 t equals 0 was 16 minus 12, that will be 4. So that is the initial condition. So we use that variable here. So to solve this equation, now we will solve this equation. How can do that? I will like make a mesh. This is a mesh 1. I1. This mesh is I1 is a Laplace because we are in the Laplace domain. We define second mesh is I2. So mesh 1 using the KVL, then 24 over S, the same way 4 I1 minus I2, this term, and plus 2 I1. Then the will be present is I1 will be 2 over 3 I2 plus 4 over S. And mesh 2, you also use KVL. Then 4 I2 minus I1 plus 1 of SC. I2 going through this path. This impedance 1 of SC. So this is I2, and we met the voltage source is 4 over S. That should be the 0 because of KVL. So from here we get the simple equation is 1 over SC plus 4 and I2 means minus 4 over S plus 4 I1. We say this is equation 1 and equation 2. Then we will do this. I don't know, make it more simple. Like that. Then the result to 1 over SC plus 4 I2 equal minus 4 over S plus 8 over 3 I2 plus 16 over S. So 1 over SC plus 4 over S and 3 over no. We do this, then 12 over S. Therefore I2 is 9 S plus 3 over 4C. Therefore VOS was VOS. This is VOS. VOS is voltage of between in this and this. Therefore that is 1 over SC I2S plus 4 over S. So there is 1 over SC 9s plus 4c3 plus 4 over s. They can be more simplified. 9 over c s plus 3 over 4c and plus 4 over s. So we need to simplify this. This is r1 s plus 3 over 4c plus 4s. This is r2. Then what is R1? The R1 is S plus 3 4c 9 over c. Here s is 0. So then digital towards 9 over c and 3 over 4c was 36 and 3. So it is 12. And R2 was s plus 3 over 4c and s plus 3 over 4c 9 over c and s is minus 3 over 4c. The then digital 2 was minus 12. Therefore, they can be represented as s 12 and 4 16 minus s plus 3 over 4c and r2 was 12 minus 12. So that's your result. Then what should we do? The last step was inverse. Last step is inverse Laplace transform. Then VOT was inverse Laplace of VO Laplace. Inverse Laplace was 16 over s minus 12 over s plus 3 over 4c. So that will be 16 minus 12 exponential minus 3 over 4ct in volts, and time is less than t. They're compared to the output values. So therefore, that values to be same with that values. So first 3 over 4c was 0.26. Therefore, c was 1.25 farad. So this is the way how to solve the elliptic equations in elliptic circuit using the Laplace transformation.